Good morning, my dear students. So coming to the problem section, today in this lecture video I'm going to solve numerical problems. Okay, so in the previous lecture, you studied what the beams and what are the importance of beams and different types of beams, and we derived the element stiffness matrix for beam element. Okay, so before solving this problem you have to remember the list of formula first. Okay, that is the what is the formula for element stiffness matrix for beam element. Okay, that is EI by LQ, that 12 6. Okay, that you have to remember, and the load due to UDL, that formula also you have to remember. Okay, so so before solving this I told the element stiffness matrix for beam element formula you have to remember, and the force due to UDL, that you have to remember. Okay, so this is what the syllabus. Okay, so here this question is very important. This question I taken from the university examination only. Okay, so question given like this. Okay, below figure, what here the below figure shows a simply supported beam subjected to a UDL. So look at here, the UDL is given. So UDL nothing but what, uniformly distributed load across the beam element. Such component we are going to call as UDL. Okay, so obtain its maximum deflection and take the Young modulus is equal to 200 gigapascal, and the moment of inertia is equal to I is equal to 2 into 10 to the power of 6 mm to the power of 4. Okay, so here so once in the given in the beam chapter, that is in the module 3, so we have in the formula we have the EI by L cube. Okay, first you have to read the question carefully, observe the diagram, so which quantity they are given. Okay, so suppose if they are not given Young modulus or moment of inertia, means you have to calculate. Okay, so here, so because in the formula we have what, EI by L cube, so Young modulus is given, I is equal to given. Okay, so here the Young modulus is substitute here, I will note down the given data first. Okay, so in this model, so you have to convert all the given data into kilonewton per meter square. Okay, in the trusses problem what you did is you converted into Newton per mm square, but here kilonewton per meter square you have to convert for easy simplification. Okay, E is equal to, so Young modulus is given 200 Newton per mm square, so you have to convert this into kilonewton per meter square, means you have to multiply this 10 to the power of 6 by 10 to the power of 3. Okay, so moment of inertia is equal to the given, so 2 into 10 to the power of 6 mm to the power of 4. So if you convert to only the m to the power of 4, means you have to multiply this 10 to the meter, means or 10 to the power of 3. Okay, so you have to multiply these two, so you are going to get the 400 kilonewton per meter square. Okay, so this required EI is required for calculating the beam problem. Okay, so here again same procedure what you followed in the truss problem or the previous case, that is the module 2. So in the module what is the first step? So finite element model you have to build here. So already I told in the while derivation, so each node having one, this V1 is called as a translation rotation, and this one is theta 1 is called as a rotational. Okay, so V1 theta 1 is the degree of freedom. Okay, so along with that we have the F1 force, always you consider vertical, and theta 1 what the M1 moment. Okay, so moment takes place due to displacement, momentum takes place. Okay, so here at the node number 1, so V1 theta 1, so the degree of freedom F1 M1, here at node number 2 M2 theta 2 V2 F2. Okay, so look at in the diagram, observe here. So here they given uniformly distributed load is equal to, we denoted by P naught, so they given symbol is toward this side beam, so consider as negative. Okay, so this UDL is acting on the beam, so consider as negative. The length is given 1 meter. Okay, so already we have the formula, we derived this equation, that is element stiffness matrix for beam element is what, K is equal to EI by L cube, so 12 6 L minus 12 6x. Okay, we already derived this, and already I told you how to remember this formula. Okay, so here in the given problem only one element is there, so we have to calculate the stiffness matrix for only one element. Okay, so since length is equal to 1, so for first element, so where L is equal to L1 is equal to 1 meter, we have the formula this. Okay, so here we have the element stiffness matrix for beam element, we have the formula for this. So length is given 1 meter, substitute wherever L is there, put here 1. Okay, so after putting the 1, so already we calculated this EI by L cube, so EI is equal to 400, length is 1, substitute here, you are going to get 400. Okay, so L is equal to 1, so substitute here L is equal to 1, so you are going to get like this. Okay, so at node number 1, so what are the degree of freedom? V1 theta 1, V2 theta 2, V1 theta 1, V2 theta 1 theta 2. Okay, so this V1 theta 1 at node number 1, V2 theta 2 is at node number 2. Okay, so this is very important, degree of freedom. Okay, so since it is single element, there is much not complicated. Okay, if you solve the two element, means it is required, the degree of freedom plays a very important role there. Okay, so coming to the global displacement vector, so here the nodal displacement vector is equal to what? So since it is belongs to one element, that is U is equal to or Q is equal to V1 theta 1 V2 theta 2 transpose. Okay, so global load vector here is equal to what? F1 M1 F2 M2. Okay, so we already derived the load due to UDL. So UDL means we have this formula, that is P naught LE by 2, P naught LE square by 12. So already we derived this equation. Okay, so here we know the formula, that is we know the P naught value, that is a distributed load. P naught nothing but distributed load, they given minus 12, length is 1. Substitute here, okay, L is equal to 1, P naught is equal to minus 12 kilonewton meter. So substitute here, so we are going to get minus 6, minus 1, minus 6, 1. Okay, that is F1, F2, F3, F4. Okay, so after calculating this, so you substitute the equilibrium condition. So we have the equilibrium condition Ku, which is equal to F. Okay, so K is nothing but what we already calculated this equation. Okay, so substitute all the values, displacement V1 theta 1, V2 theta 2, and force minus 6, minus 1, minus 6, plus 1. Okay, already we calculated this. Okay, so after this you apply the boundary condition here from the diagram. Okay, so in the from the diagram, so at node number 1 is fixed is there, so that is V1 theta 1 you have to did it like this: first row first column and second row second column. Okay, at node number 2 ruler support is there, so ruler support means along the x direction moment takes place, so vertical, that is V2 going to delete this, and this the third V2 you are going to delete, so remaining is what minus 6 theta 2. Okay, so that you need to calculate. Okay, so that is 400 theta 2, which is equal to plus 1. Okay, so in that is what in the next equation. So applying the boundary condition here. Okay, so in the look at the diagram, so V1 theta 1 V2 are going to fix, that is there is no movement. So with the help of using elimination method, we have to delete the respective row and column, so remaining is 400 into 4 theta 2, which is equal to 1. So from this, theta 2 is equal to 6.25 into 10 to the power of 4. The theta unit is radian. Okay, so we calculated the theta 2. Okay, so therefore the final nodal displacement are what? So V1 theta 1, V2 theta 2. So this is 0, this is 0, this is 0, because it is fixed this here. So we already calculated theta 2 is equal to 6.25 into 10 to the power of minus 4. Okay, so this is what the displacement we need to calculate, how we are going to calculate it like this. Okay, so now, so V1 theta 1, V2 theta 2 we calculated here. Okay, by using elimination method. Okay, so coming to the, they are asking to find the maximum deflection. Okay, so how to calculate the maximum deflection is nothing but, so already we have the formula. Okay, always at the midpoint we have the formula. So before solving I told you the list of formula, go there. Okay, we have the formula V is equal to H into Q. Okay, where H stands for the Hermite shape function. Okay, so H1 is equal to what? We have this formula. Okay, so V is equal to H1 V1. Okay, half of H2, that is length LE by 2 H2 theta 1 plus H3 V2 plus LE H2 H4 theta 2. Okay, so where H1 H2 H3 H4 are called as Hermite shape function of the beam element. Okay, so but at the midpoint the zeta is equal to 0 according to the what, the natural coordinate system. Okay, right. Okay, so at midpoint zeta is equal to 0. From the boundary condition we have the V1 theta 1 V2 is 0. Okay, substitute these values in the in this equation. So remaining is what? The maximum deflection. V stands for here maximum deflection is equal to what? LE by 2. Okay, so H2 H4 theta 2. So this is the what? The maximum deflection after substituting the all the values here. Okay, so here H4 already we have the formula for H4. H4 is equal to what? Minus 1 minus zeta plus zeta square plus zeta q whole by 4 theta 2. Okay, already we derived this at the middle of the Hermite shape function. Okay, so now we have the zeta value, that is 0. So the L is value we have, theta 2 value also we have. Okay, substitute all the values, we are going to get the maximum deflection is equal to 7.8125 into 10 to the power of 5 meter. Like this you have to what? Calculate the maximum deflection in the given problem. Okay, so this is very important problem. I hope you understand this. Okay, so before solving the any beams problem, you have to remember the first formula this. Okay, so this is very important formula, and formula due to UDL. Okay, so how to remember this means, look at here. Okay, this 12 you write. Okay, so these four quantity write as it is this side. Okay, so that is 12 minus that is 6 LE 4 LE square. Okay, just to opposite you have to put the sign. Okay, so opposite you have to put the sign. So again coming to this, write this minus 12 6 LE minus 6 LE 2 LE. So this you write this side. So here put the negative sign, this side means you have to put the here opposite sign. Okay, so like this you have to remember this formula. Okay, element stiffness matrix for beam element. Okay, so in the beam chapter this derivation is very important. Okay, question they may ask you like this: derive the element stiffness matrix for beam element using Euler-Bernoulli theorem or any one method. If nothing is mentioned means you can use the Cartesian coordinate, that is very simple method. Okay, so this is what the beam, and one more thing is you have to remember this. Okay, so in the given question the load is given what? The load due to UDL. Okay, so already we derived the load due to UDL, we have the formula like this. Okay, so here the P naught value is given and length is value already given. Substitute here, you are going to get these values. Okay, so this is about the what the element stiffness, that is what the stiffness determination of the deflection at midpoint. Okay, at the final stage also, that is the final, this formula is also very important here. Okay, so here the maximum deflection, we have the formula V is equal to HQ. So H is the Hermite shape function, we derived this, substitute here. Okay, from the given condition, so zeta is equal to 0, v1 theta 1 v2 is equal to 0 from the boundary condition, substitute here, the remaining is we are going to get the maximum deflection in this formula. So H4 we have the formula, that is -1 minus zeta. So zeta value substitute here and length value and theta value substitute in this, we are going to get the maximum deflection is equal to this. Okay, so like this you have to calculate the maximum deflection for the given beam problem. Okay, so this most important problem for the point of examination. Okay, so I hope you understand this problem. Okay, so thank you.